Hello everyone, welcome back. Today I am starting the contains duplicate series here on DKodeTree. The first problem in this series is Leetcode 217 contains duplicate. It's fairly a simple problem, but it can be solved in multiple ways, and understanding these approaches will definitely help strengthen your DSA fundamentals. I will walk you through the different methods, their complexity analysis, and then we will quickly code up the optimized solution. We are given an integer array as input and we need to determine if it contains any element more than once. That is, if any value appears at least twice in the array. The easiest way to solve this problem is by taking each number one by one and checking if it matches any of the remaining numbers. In this example, we start with 1 and then compare it with the remaining elements 2, 3 and 2. We can see that 1 does not match 2, it doesn't match 3 and it does not match the last 2 as well. So we are done checking for 1. Next we pick the element 2 and compare it with the remaining elements. We can see that 2 does not match 3 but it does match the next 2. So we have found a duplicate and we can return the result as true. Note that we don't need to compare 2 with 1 since we have already compared 1 with 2 earlier in the previous iteration. In this approach, by comparing only forward and not backward, we avoid unnecessary comparisons. In this brute force approach, as we are comparing each element with all the elements that come after it, and comparing one element with the remaining elements takes O of n time. And since we do this for all n elements, the overall time complexity becomes quadratic, that is O of n squared. And as we are not using any extra space in this approach, so the space complexity is O of 1. However, implementing this approach on Leetcode usually results in a time limit exceeded error, so we definitely need to look at a more efficient solution. The next solution that can improve the time complexity is sorting, but the space complexity may increase depending on how sorting is implemented in a given language. Let's say we simply sort this input array. So if the input is 1, 2, 3, 2, after sorting it will become 1, 2, 2, 3. Notice that in a sorted array, any duplicates will appear next to each other, that is at adjacent positions. So after sorting, we can do a single pass through the array and compare each element to the adjacent one. If we find a match, we immediately return true, that is a duplicate exists. And if we finish the scanning without finding any matching adjacent elements, we return false. For example, first we will start with 1 and then check if it matches its neighboring element 2 or not. And it does not match, so we move to the next element. Now we are at 2 and we will match 2 with its neighboring element. And we can see that these two are actually equal. That implies we have found a duplicate and we can directly return true. And if we finish scanning the entire array without finding any matching adjacent elements, then we return false. The time taken to sort the input is at least O of n log n when using the best known sorting algorithms or any efficient built-in sorting function which are generally implemented to run in O of n log n time. And for scanning the list, it will take O of n extra time. So we can see that the total time complexity is dominated by the sorting portion, which comes down to O of n log n. The space complexity also depends on the way the sorting is implemented. If the sorting is done in place, then the space complexity is O of 1. And if it uses extra space, like merge sort, it can go up to O of n. Apart from that, we haven't used any additional space in this approach. Can we do any better? And it turns out yes, we can. We can use hashing to reduce the time complexity to O of n. However, we need to trade off some space for time because hashing needs additional memory as well. There are multiple ways to solve this problem using hashing, but almost all of them have the same time and space complexity. One optimal way is to use a hash set which can solve this problem in a single pass. While iterating through this list, we can use this set to keep track of the elements that we have already seen. If we encounter a duplicate element, we can simply check if it is already in our hash set or not. And if it is already there, then we know it's a duplicate. Suppose this is our hash set, which is initially empty, and we start scanning our list from the first element, which is 1. We will check if 1 is already in the hash set or not. It is not. So obviously this is not a duplicate. Now we'll add it to our hash set. So we have added 1. Now we move to the second element, that is 2. And we check if it is in our hash set or not. Still it is not in our hash set. So we will add it to the set again. So this is 2. Next we move to our third element, which is 3. We again check if it is in our hash set or not, but there is no 3 in the hash set. So this is also not a duplicate element, and we add 3 in our hash set. So that next time when we see a 3, we can detect it as duplicate. Now we are at the last element, which is 2, and we can see that in our hash set another 2 already exists. This implies that it is a duplicate element, and so we will directly return true. And even after scanning the entire list, if we haven't found any duplicate, then we would have returned false. Since we are scanning the list only once, so our time complexity is O of n, and the only extra space that we are using is for the hash set, and in worst case all the elements can go inside the hash set. So the space complexity is also O of n. Now let's code this up quickly. After that I will show you a super simple one-liner solution to this problem as well. So for the hash set approach, which is the optimized solution, we will create a set initially for storing all the scene values. Now we'll iterate through each number in the input array using a for loop. So for num in nums, and then check that the current number is already in the scene values or not, which we can easily check using if num in values seen, we will directly return true, which implies that the current value is a duplicate. Otherwise, we will go ahead and add the current value to the hash set. Finally, if we haven't seen any duplicate number after completing our iterations, then we will return false. Now let's run this. So we can see that this is accepted. That's all we need to do. It works efficiently and is considered the optimal approach. But guess what? We can actually solve this in just one line of Python. Think about it. If the length of the input list is greater than the number of unique elements in it, then definitely there must be duplicates. Otherwise, all elements are distinct. So here is the one-liner. Return len of nums is greater than len of set of nums. So if we convert the list nums into a set, it will automatically remove all the duplicates and only keep the unique elements. So all we need to do is to compare the length of the original list with the length of the set. We can see that this is also accepted. It's showing a bit faster, but complexity wise, this approach is no different from the previous hash set based solution, because converting a list into set takes O of n time and O of n space to store the new set in the worst case. I have added the code implementations for all these different solutions on my website DKodeTree.com. Feel free to check them out if you'd like to explore the codes. It's completely free and no login is needed to access the content. In the next video, I will be covering contains duplicate 2, discussing both the hashing and sliding window approaches and then coding up the sliding window solution. So stay tuned. If you found this helpful, don't forget to like the video and subscribe to the channel. Till then, take care and I will see you in the next one.